Hi everyone, in this section we'll start 10.11, angular momentum. So if you recall, we've been looking at how every rotational quantity has an analogous linear quantity. And I want to do the same thing here for momentum. So we started out by saying that torque is defined by position vector r from the axis of rotation cross f. And we can define angular momentum in the same way. Angular momentum has symbol L, and it's given by r cross p, where p is the linear momentum. We can go further and say that angular momentum is r cross mv, since mv, mass times velocity, is the definition of our linear momentum. Just a couple notes here. The units for linear momentum were kilogram meters per second. Now, because we're crossing with this other factor of r, we have units of kilogram meters squared per second for angular momentum. I'll just move so you can see that. Okay, and the other thing is that this is a cross product, so we're going to end up with a third vector perpendicular to the two that we're crossing. So the angular momentum will always be perpendicular to both the position and the velocity of that object or of the point in question. And so far we've looked mostly at circular motion, where we had a velocity that was tangential to the motion, but it doesn't depend on that. So as wherever the position vector and the velocity vector are, this will produce a third vector perpendicular to both of them. And if it's rotating in the xy plane, then we will always end up with our angular momentum along the z-axis. Okay, another important relationship that we looked at is Newton's second law in terms of momentum. So we found that the net force acting on a system or an object is equal to the derivative of momentum with respect to time. What I want to prove is that we do have this same relationship in the analogous form for rotational motion, and it looks like this box. So the net torque is equal to the derivative of the angular momentum with respect to time. And I'll show you why. So if we start with the derivative of angular momentum, dl by dt, we just showed that angular momentum is r cross mv, so let's take the time derivative of that. d by dt, r cross mv. So we have a product rule. We can apply the product rule for derivatives. So derivative of the first times the second plus the first times the derivative of the second. So we have dr by dt cross mv plus r cross mdv by dt. And then plugging in some quantities that we know here, dr by dt, that is the velocity. Then also we have dv by dt, which is the acceleration. Now look, we have velocity cross m times velocity. So those vectors will be parallel. And if you cross any two parallel vectors, you get 0. So this first term is 0. Then we have r cross f net. So we end up with our time derivative of angular momentum equals r cross f net. So careful here, if we have many forces acting on a system, in order to do r cross f net, we have to actually do r cross f for each individual force, since they're at different positions from the pivot point, and sum those vectors. So we'll take the sum of r cross f, and that gives us the net torque. So this is the definition, and this is why we can have a net force that's 0, but a non-zero net torque. But anyway, this sum is the net torque, which is what I was getting at. So what we're left with is this important relationship that the net torque acting on an object is equal to the derivative of that object's angular momentum. Okay, let's consider a rigid body that's made up of many individual mass elements of mass mi, or mass particles, and we want to find the total angular momentum for that rigid body. What we can do is find the angular momentum for each particle element using our definition of r cross mv. So we have ri cross mi vi. And let's consider for now that these particles are only moving at components with velocity components that are tangential to the r vector. So we have are at a tangential velocity, which means it's perpendicular to the r vector. So we'll have ri mi vi sine 90. And then that sine 90 is 1. So ri mi vi, and then we can plug in for v equals omega r, the angular velocity, times r. Look, we have two factors of r, so we can combine them, so mi ri squared. and that's that individual moment of inertia for that particle. Then we have times omega, the angular velocity. I've removed the subscript now because each individual mass element will rotate with the same angular velocity at any particular instant, since the body is connected. Okay, so then we have L equals the sum of all those individual angular momentums. So the sum of all mi/ri squared times omega. And this we know is the total moment of inertia for that body. So this gives us a really important relationship, which is that the angular momentum of the system equals I times the angular velocity, omega. Now I did say let's consider particles that only move with a tangential component of velocity. The velocity vectors of these particles, or mass elements, can have radial components of the velocity, but as long as the object is symmetric about the axis of rotation, those radial components of the velocity would cancel out. So for example, let's say that there was velocity vectors here, those two radial components would cancel out, and then we'd only end up with a net angular momentum from the tangential components anyway. So we're only assuming that it's symmetric about the axis of rotation. All right, the other important thing that this relationship shows us is that the angular momentum has the same direction as the angular velocity. And we use the right-hand rule for the cross product to find this. So just to review, what we did was curled our fingers in the direction of the rotation. So here, for example, counterclockwise, and then that gave me positive as up. And now that up direction would be for both angular velocity and the angular momentum. And then this one, if we curl our fingers the other way, we get down, and down would be the direction again of the angular velocity and the angular momentum. Okay, so before we saw a very important relationship with regard to the net external force and momentum. If the net external force acting on a system is 0, then we can say that the total momentum of the system is conserved. So that means dp by dt equals 0, and we have initial linear momentum equals final linear momentum. We can say a similar relationship for the net torque and the angular momentum. If the net external torque acting on a system is equal to 0, then the change in linear momentum for the system, or the time derivative of the linear momentum, equals 0. So that would mean that we have the initial momentum of the system equal to the final momentum of the system, as long as there's no net external torque during the motion. So let's look at how this applies to some examples. A physics professor stands at the center of a frictionless turntable with arms outstretched and a 5-kilogram dumbbell in each hand. He is set rotating about the vertical axis, making 1 revolution in 2 seconds. Find his angular velocity if he pulls the dumbbells in towards his stomach. His moment of inertia without the dumbbells is 3 kilogram meters squared with his arms outstretched, and 2.2 kilogram meters squared with his hands at his stomach. The dumbbells are 1 meter from the axis initially and 0.2 meters at the end. Okay, so in this example, we don't have a constant moment of inertia. The moment of inertia will change as the professor moves his hands inwards. It will decrease as he moves them inwards because now more of the mass is concentrated near the axis of rotation. So to start, let's calculate both of these moments of inertia, and then we'll apply angular momentum. Okay. So initially, the moment of inertia is I1 with his arms outstretched, plus then each dumbbell is at 5 kilograms, and then 1 meter from the axis of rotation. And it's just R that matters, so it's not an issue that they're on opposite sides. So we have 10 kilograms times 1 meter squared, which gives 13 kilogram meters squared for the moment of inertia. Then in the final case, we have a new moment of inertia for the professor with his arms towards himself. So we have I2. 2.2 kilogram meters squared plus 10, and now each dumbbell is at 0.2 meters that squared from the axis of rotation. And that gives 2.6 kilogram meters squared, so much lower as we would expect. And before we do angular momentum, we will need to find the initial angular velocity, and we know that initially he's rotating at a constant rate, making a period of 2 seconds. So 1 revolution is 2 pi in 2 seconds. So omega is delta theta over delta t, which is 2 pi over 2 seconds, so pi radians per second. And now there will be an angular acceleration as he brings his arms in, and that angular velocity changes. So now applying the conservation of angular momentum, since there are no external forces causing a torque in the system, we have initial angular momentum equals final angular momentum. So I1 omega 1 equals IF omega F. And then solving for that final angular velocity, we have I omega I over IF. So 13 kilogram meters per squared times pi over 2.6 kilogram meters squared, which gives a final angular velocity at a higher rate of 15.7 radians per second. Okay, let's try the next example. Example 25, a solid wood door 1 meter wide and 2 meters high is hinged along one side and has a total mass of 40 kilograms. Initially open and at rest, the door is struck at its center by a handful of sticky mud with a mass 0.5 kilograms, traveling perpendicular to the door at 12 meters per second just before impact. Find the angular speed of the door. Does the mud make a significant contribution to the moment of inertia? All right, so the door looks like this, and if you look up the table of moments of inertia, then we have, this is, I think it's called a slab rotated about one side, and the moment of inertia is 1/3 ma squared, where a is the smaller side or the width. So we have 1/3 times 40 kilograms times 1 meter squared. It's also the width from that axis of rotation, so we're choosing the opposite side for a. So we get 13.3 kilogram meters squared for the moment of inertia of the door. Now, to use conservation of angular momentum, we do need to account for the angular momentum of every object in the system. Even if you wouldn't naturally think about it rotating, it can still have angular momentum. So we need the moment of inertia of the mud, which is just a point particle, so that will be mr squared, 0.5 kilograms times 0.5 meters squared, because it's initially 0.5 meters from that door when we have its velocity. And there's no external forces, the only force, no external forces that are causing a torque. The only external forces will be between the door and the mud. So this is the initial case. We have this mud being flung at the door that's open, and this is the hinge here. And initially the door's at rest. It has an angular velocity of 0. And then initially the mud, its angular velocity can be found through v over r. So omega equals v over r. We have 12 meters per second over 0.5 meters, which is 24 radians per second. So don't forget to include those, the angular velocities of the objects in the system that we'd normally think of as moving with a translational velocity. We can still convert it using v equals omega r. Okay, so after the mud sticks to the door and it causes the door to swing, so after the system will have a final angular velocity, and that's what we're going to look at through the conservation of angular momentum. And so we have our initial angular velocity of the mud as 24 radians per second. Okay, so applying conservation of angular momentum here, we have L initial equals L final. And then initially we have I times omega for the door and the mud, and then equals the total moment of inertia after times that final angular velocity. Now, solving for that angular velocity, I'm going to cross out, we said omega d is 0, so I'll cross that out right away. We have I omega over the total moment of inertia. So 0.125 kilogram meters squared times 24 radians per second over 13.3 kilogram meters squared plus 0.125 kilogram meters squared, which gives a final angular velocity for the door of 0.223 radians per second. So our question was also, does the moment of inertia of the mud have a significant contribution here to the total moment of inertia? And well, yes and no. So if we just talk about the total final moment of inertia, I mean, not really. It's very small here. So I calculated, if we just ignored that, we got 0.225 radians per second. It does, however, have a significant contribution overall in our math, right? As if we ignored completely that moment of inertia of the mud and its angular momentum, there'd be no explanation here for the door rotating after it collides with the mud. However, we could treat this problem with linear momentum in a different way, but if we're using rotational momentum, it's important that we do account for that moment of inertia and initial angular momentum of all particles in the system. Okay, one more example. Example 26. A small block on a frictionless horizontal surface has a mass of 0.0250 kilograms. It is attached to a massless cord passing through a hole in the surface. The block is originally revolving at a distance of 0.3 meters from the hole with an angular speed of 2.85 radians per second. The cord is then pulled from below, shortening the radius of the circle in which the block revolves to 0.150 meters. Model the block as a particle. A, is the angular momentum of the block conserved? Why or why not? B, what is the new angular speed? C, find the change in kinetic energy of the block. And D, how much work is done in pulling the cord? All right, so first question here, is angular momentum conserved throughout this motion? We have this surface here, and then the block is rotating on that surface at an initial radius. This cord is pulled down, which shortens the radius for that block, and it continues rotating. Now, there is an external force that's pulling down on this rope in order to shorten it, but yes, got it up here. So yes, angular momentum still is conserved, and that's because the net torque is still equal to zero, the net external torque at least, because it's through this axis of rotation, so it's at r equals 0, so that external force does not cause a net torque. All right, so in order to solve for part B, we're going to need to find the moment of inertia for the mass in each position. So for this point mass, we can use I equals mRI squared. And so initially it's 0.250 kilograms times 0.3 meters squared, and that gives 2.25 times 10 to the negative 3 kilograms meters squared. And then in the final case, it's m times rf squared, which is 0.150 meters squared, and that gives 5.625 times 10 to the negative 4 kilogram meters squared. So with those two moments of inertia, then we can determine the final angular velocity for the rotation. Applying conservation of angular momentum, we have I initial omega initial equals IF omega F, and then we can solve for omega F, which will be I omega I over IF. So 2.25 times 10 to the negative 3 kilogram meters squared over 2.85 radians per second, which gives us, dividing by the final moment of inertia, 5.625 times 10 to the negative 4 kilogram meters squared, gives a final angular velocity of 11.4 radians per second. And I'll just erase, and then we can use this to find the change in kinetic energy during the motion. So with those two angular velocities, we can just plug them in now to find the change in rotational kinetic energy. Delta K is 1/2 IF omega F squared minus 1/2 II omega I squared. So plugging that in, we have 1/2 that final moment of inertia times 11.4 radians per second squared minus 1/2 the initial moment of inertia times 2.85 radians per second squared to get a change in kinetic energy during the motion of 0.0274 joules. And this is a change in rotational kinetic energy, but we've shown how we could convert it to a change in translational kinetic energy with B equals omega R and plugging that in. So for part D, what is the net work done during this motion? Because of the work kinetic energy theorem, this has to be equal to the total change in kinetic energy, which we have in the form of rotational kinetic energy this time. So the net work done is also equal to 0.0274 joules. Okay, and that's our last example, so let me know if you have any questions for this section.